Okay, so you should be seeing our virtual meme of the day. This is kind of an ongoing thing. I just surf the web and look for funny stuff that's school appropriate on virtual learning. So the virtual meme of the day, I forget who this gentleman is. He's like an older kind of a talk show host. You said you finished the assignment on time, but the Google revision history said otherwise. So I can see when stuff is turned in. I thought that was kind of funny, kind of quite humorous there. But all right, so let's go ahead and jump into our daily question. I've got two of them here, so I would like you to go ahead and type in the chat box and respond to this question. So this was from our POGIL, and remember our ecological pyramids POGIL was due today, as well as that Edpuzzle video on energy pyramids as well. So make sure you turn those in. So I want you to think about, is the producer's level in the two pyramids of numbers, so the bottom level, referring to the same organisms or different organisms? So are the oak trees and the oak leaves the same organisms, or are they different? So go ahead and type that in the chat box right now if you would. Thank you. And I will take attendance. All right, so let's get some responses in there, please. Do we think it is the same organism, different organism? Okay, thank you, Ethan, for getting the ball rolling. Awesome, awesome. All right, so kind of a trick question, and don't want to give the answer yet. So think about that. Are leaves in a tree different organisms, or are they part of the same organism? All right, so good showing for different so far. All right, different. Thank you, Wade. Different. All right, so let's go ahead and take a look at this one. So there's a large showing for different. However, these actually are going to be a part of the same organism. So oak trees, the entire tree itself is the same organism. It just consists of, and the leaves are just different parts of that organism. So within each oak tree itself, like one oak tree from another would be different organisms. But if we looked at all the leaves on those organisms, they would be a part of those organisms, right? They're just the photosynthetic units. The leaves allow the tree to make energy, to photosynthesize. And B kind of makes it a little bit more helpful, because when we see how many leaves there are, we can see how much energy is available to these caterpillars, which eat the leaves. Whereas if we just have two oak trees, that might seem like not a whole lot of energy to be passed on to these caterpillars. All right, next question. Which of the two pyramids in Model 2 gives a more accurate amount of what occurs in the ecosystem? So which one do we think? A or B? It's kind of based on what I was talking about there. A or B? A more accurate representation of what's happening. All right, I'm seeing some B's. Great, great. I had to go with a two-screen setup today so I can see the chat box on one computer and then I can see my presentation on another. That's kind of the lifestyle we're living in these days, a two-screen lifestyle. All right, so I see a good showing for B. That is fantastic. All right, so it is going to be B, and it's really, this is somewhat up to debate, because while Pyramid A is a completely valid response, essentially it is still a pyramid of numbers. It only shows the two oak trees as a whole. It doesn't talk about all the photosynthetic units, the leaves, all the energy that the leaves could give to these caterpillars. A traditional pyramid does have a really large bottom tier or bottom level. We see that here. So this way, when we talk about all the individual leaves that provide energy to our herbivores, it really makes it look like more of our traditional pyramid than if we just talk about the two trees as a whole. All right, cool. All right, so we're gonna now move on and talk about energy transfers. So our next topic is gonna be on energy transfers. We're gonna work on another POGIL today, and you're gonna see we're gonna be doing a lot of POGILs this week because it's kind of just a good guided way to work through some different activities and lessons that a lecture might be kind of not so interesting. So I'd like you to go to Google Classroom right now. I will present this to you. So go to Google Classroom, you are third hour, and please type in the chat box at any time or blurt it out if you have questions. Feel free. So the assignment you're looking for is right here, Thursday, October 22nd, which is today. And it's fairly simple, not as crazy as a lot of my posts look in terms of like a lot of links. All you're going to do is you're going to click on this energy transfer POGIL. That will be the homework for tonight. Kind of a quick turnaround on this one, but we're going to spend essentially the whole hour working through this one. So energy transfer POGIL. So that's what I want you to click on. And I'd also like you to get out a calculator of some sort. And if you don't have a calculator, then you can use your phone, or you can just type in stuff on Google. I actually found out my graphing calculator was out of batteries. But okay, so get out a calculator, find that document. And before we start getting into that document, I want to pose the question, what is the law of conservation of energy? And does energy ever really disappear on Earth? So go ahead, if you want to talk about that, feel free to unmute yourself. Feel free to type that in the chat box. So what is the law of conservation of energy? If we know. So what does it mean to conserve? What do we think it means to conserve? All right, great response, Olivia. No energy is wasted, and it is all reused, is what Olivia said. Awesome, yes. So essentially, that is correct. So all energy on Earth never really leaves Earth for the most part. There is some that is radiated back into space, but it's mostly a closed system. So the energy never really disappears. It's converted from one form to another. And Abram summed it up as well. Energy can't be destroyed. It is transferred from one form to another. So essentially, this is what the law of conservation of energy states. Energy cannot be created or destroyed. Energy may change form, but the total amount remains the same. So we're going to see that during life processes like digestion, a lot of energy seems like it's lost, like that 90% that isn't passed from one trophic level to another. However, it's actually going to go to be given off as heat, be used to produce biomass, so on and so forth. So you can see as we take in food, we give off heat, we have to excrete waste, we metabolize and give off heat doing that. So there's a lot of energy transfers happening in our body every day. Okay, so now you should be on that POGIL. I'm going to go ahead and launch that and present it to you. And we are going to take the rest of the time. So I'm going to be with you the rest of the time. And we're going to work through this POGIL. And whatever we don't get through, oh, I don't want to show you the key. Let me make sure I've got, and I will present this instead. I don't want to show you the key. Oh, that's the key as well. Let's actually find something that's not the key. Energy transfer POGIL. This is not the key. Good. And I've got to make a copy of this. Bear with me here for a second. I thought that link was working. Apparently it was not. That's okay. All right. So I will now share the correct one with you. I apologize for all the tab jockeying. Copy of energy transfer POGIL. Let me know if anyone, no, this is the key again. I don't want that. Here we go. This is what I want. Let's just get rid of that key right away. This is what I want. Can anyone not see that? So this is what you should be seeing. You'll see in red throughout your sheet, I've added some formulas that will be helpful for you to complete this, and we'll walk through some of them. All right, so I'm going to go ahead and read the first passage. So this POGIL is called Energy Transfer in Living Organisms, and I'll make it a little bit bigger so you can see it. How does energy move through an organism? The law of conservation of energy states that energy can neither be created nor destroyed. It can only be transferred to another form. In living things, energy is transferred as organic matter, molecules of carbohydrates, fats, starch, etc. But does an organism use all of the energy that is provided by the organic matter available? How is the law of conservation of energy applied to living organisms? Okay, so we're going to first begin by starting with Model 1. And Model 1 describes food conversion in a herbivore. All right, so an herbivore, something that eats producers. We could think about a cow. The cow will be an example organism throughout this presentation. So let's go ahead and think about this. According to Model 1, how many grams of grass does herbivore A eat each day? So I would like you to type that into the chat box. So based on that model, how much? Thank you, Isabel. Thank you, Skylar. Cool. Awesome. And feel free, I'm giving away answers, but I'm perfectly happy. This is not an easy POGIL to just like go through by yourself. So I wanted to make sure we do at least half of it together. So just go ahead and type that in. And where I'm getting that from is grass ingested per day is 4 grams, right? So no hidden answers here. Most of them are just going to be given right here in your figure. Okay. All right. Refer to Model 1. How much did herbivore A grow from eating this grass? So if you know that, type it in the chat box. All right, great. I am seeing that you guys seem to be understanding this so far. We've got a good showing going on here. Thank you, Megan. So herbivore A grew 0.64 grams. 0.64 grams from eating this. And essentially, we know that because it is called biomass increase. So the term used to represent growth in Model 1 is biomass increase. So when I eat a cheeseburger at McDonald's, which I usually don't go to McDonald's, my biomass would increase, maybe a little bit more than I would like, because the weight or the mass I'd gain outweighs the mass I would lose from like the waste I would produce. All right. So what do we think is meant by egested waste? Egested is a weird word, and I wish they wouldn't have used it in this POGIL. What is meant by the egested waste here? So go ahead and type that in the chat box if you got a thought, or you can say it aloud if you'd like. Egested waste. The process of discharging undigested waste material. Absolutely. Absolutely. So essentially, it's whatever is excreted. So it is waste that is excreted. Waste excreted, this is probably going to be fecal material or poop, You might laugh, but that's essentially what it is. And urine, right? That's what it's going to be. That's what it's going to be. So these are the actual kind of solid and liquid waste excreted each day. You can see it's 2.4 grams here. So over half of the weight of the grass ingested was egested as waste. All right, so now we can think about number 4. Is all of the mass of the ingested grass accounted for in the growth and waste of herbivore A? If not, how much is missing? So I would like you to think about, based on our 4 grams, so if we have 4 grams that go in, and we subtract 2.4, which is the egested waste, and we subtract how much biomass it gains, which is 0.64, do we still have extra stuff? Do we still have extra stuff? Or has all of our 4 grams been used? So essentially what I'm asking is this answer 0, or is it an actual mathematical value? Do we have anything left? Gentlemen, we got to make sure we keep the chat respectful, please. Keep the chat respectful, please. All right. So essentially what we got here is we have going to have extra mass left here. We're going to have extra mass left here. So we have to go ahead and figure out what extra mass is not accounted for. The extra mass, it turns out, is going to be this 0.96 grams. The 0.96 grams is going to be how much is left over. So where did that come from? Where do we find 0.96 grams in our figure? Can somebody tell me? Can somebody perhaps unmute and tell me where we're seeing that 0.96 grams, or put it in the chat box, please? On the left, yes, on the left. Thank you, Skylar. So, and I think what Skylar meant is on the left of the diagram. So it is waste from respiration, cellular respiration. Now, we haven't talked a whole lot about that. So for number 5, in addition to growth and waste production, what else does herbivore A's body do with the food it ingests? It undergoes cellular respiration to metabolize or break down the food. So that is a process that's not accounted for by just how much liquid and solid waste is going out and how much the cow is growing. That's separate. So we want to make sure all the energy is not destroyed. We want to make sure that it is going somewhere. Okay. Number 6, as cells undergo cellular respiration, what products are produced and how are they released from the body? So what do we think? When we breathe in, what do we breathe out? What are the products of cellular respiration? What do we think for that one? Yep, CO2 is definitely one of them. CO2. CO2 is a good one. What else? Any other thoughts there? Any other thoughts? And water, yes, water. Yes, indeed. CO2 and water are produced as the waste products. So the CO2 mostly comes from the actual exhaling. So from our lungs exhale. The water, how do we excrete the water? It's going to be in the form of urine, right? It's going to be from our kidneys. Our kidneys filter out, the blood and filter out that waste from the bladder, actually, specifically, right? Oh, good question, Seth. How do I make the small 2? In order to make the small 2, you hit, and I'm so used to doing it that I kind of don't even think about it anymore. You hit Command, okay, yeah, Command key and the comma key simultaneously at the same time. That's how you make a subscript, and to make a superscript, command and period at the same time. Yes, that's something that is very good. And you guys might not have the command key. Good question. So it's probably the control key for Chromebooks, right, Abram? Thank you for helping me with that, because it's all different for you folks. I'm used to using the control key as well. Command is something that is specific to Macs. So that's an adjustment. All right, so moving on. Number 7. 7 has been already done for you. So draw an arrow in Model 1 to represent respiration and label it. So essentially, if this were a written POGIL, you would have drawn the arrow on here, but it's already been done for you. So drawing is going to be kind of hard to do on this online format. Model 2, moving on. Let's go ahead and look at that. So now we actually start looking at the energy being used. So what unit of energy is used in Model 2? What do we see? Think about the nutrition facts labels that you'd see on, say, a Pop-Tart box. What is our unit? Ethan, thank you. Any other thoughts on what our unit is? Abram, thank you so much. It's going to be kilocalories, if I can type it, or abbreviated as kcal. Just the small calories are so insignificantly small that we don't really measure them because, you know, it would be like thousands or millions of small calories. So we use kilo as a more efficient way to do that, to essentially get that to work out, get the math to work out. Okay. All right, so jumping back in. So refer to the energy value of the ingested grass in Model 2. What is the energy value of the grass eaten by herbivore A each day? So how much energy does it get? How much energy is ingested by herbivore A? What do we think? Chat box. Is it 5? Is it 0.33? What is it? Yeah. Thank you, Butterfly. Yes, it's 0.8. 0.8 is how many calories, or I should say kilocalories. I got to be specific, right? Units are super important. All right. Yes, indeed. Now, what's the energy value of the grass eaten by herbivore B then? You're just going to look at the same place you would on the other figure. It's the grass ingested, 5 kilocalories. 5 kilocalories. Awesome. You guys are doing great. You guys are following along real well. All right, energy value. So based on the difference, the disparities we see in those two numbers, 0.8 and 5 kilocalories, which herbivore would you predict to be the larger animal? Which one? A, B? Not really a trick question at all, right? You would predict, right? You would predict it to be B. Now, it doesn't necessarily mean B is, because we're going to look at the energy efficiency, how efficient is the energy used. But you would predict it's going to be B, because essentially looking at nothing else but what is being taken in, this is consuming more than 5 times the amount of calories. So that would be like me versus Michael Phelps, right? Michael Phelps during the Olympics consumed like 11,000 calories a day, which is crazy. And I probably only consume about, I don't know, 3,000 or whatever. But depends on the day. All right, number 10. In Model 2, what are the 3 ways that the energy taken in by herbivores is used? Okay, so essentially we're looking at not this arrow, but what are the 3 pathways? What can happen? So name a pathway. All right, we got all 3. Thank you, Katie. All right. That egested waste essentially means excreted waste. Like ingest, to ingest something is to take it in. To egest is to send it out. I guess that's maybe what they were thinking there. Yeah, so we can go ahead and think about it as such. We can think about it as respiration, heat loss, and egested waste. It doesn't matter in what order. These aren't necessarily done in a particular order in the organism. Waste can be produced while heat is being lost. It's not like a recipe. Like first you got to digest, then you lose your heat. No, it's It's happening all simultaneously, and we don't even think about it, right? Which is pretty awesome. Okay, number 11. So now I've started to put some formulas in here to really support you in like knowing what to do here, because a lot of these start to get more mathematical. So for each herbivore, calculate the total energy output. So for herbivore A, the energy output essentially is how much energy is lost to the environment. So we would just take our respiration values, our heat loss values, and our excreted waste values. So add that up. Let's see what we can get. So add them up, see what you get. Take a moment to do that. I'll go ahead and present my calculator. Show you what I'm doing, because I don't have a calculator right in front of me, which I probably should, but it is going to be, and then I got to reference the value, 0.33 plus 0.228 plus, and our last one is going to be 0.192 calories. So we get a total of 0.75 kilocalories. So jumping back into the correct one, let me jump back in. 0.75 kilocalories, right? That is how much. So if you'd like, you can type in the math that goes along with it, but you don't absolutely have to, okay? All right, so then herbivore B, I would like you guys to do this on your own. So go ahead and do that. Add up all the values. So you'll add up the 1.6, 1.4, 1.25. Go ahead and put your answer in the box and type that into the chat box so we know what that is. This one you might be able to do in your head. So let's see what you get. Let's see your responses. Nice. I love the units too, Olivia and Butterfly. Good units. 4.25 kilocalories. And Isabel, thank you. All right. Yes. So that is how much energy is lost to the environment, essentially. When you think about it, that's not all that efficient, because we're losing a lot to the environment. Can't we make the human body or a cow's body a more well-oiled machine? Well, it turns out that we can only be as efficient as we can be. There's not much of a way to decrease the efficiency. So number 12, does the total amount of energy output for each herbivore add up to the total amount of energy eaten by each herbivore? So essentially, does the 4.25, does it match up to the 5, or is there something missing there? What's missing? So is 4.25 and 5 identical? Answer me that. It is not, right? It is not. So no, essentially the answer that you need here is no. There's no explanation that needs to happen there. The other questions kind of get at what this difference is. So what is going to happen with that extra, with that leftover energy? So here there's going to be a 0.05 difference between 0.08 and 0.075. Here there's going to be a 0.75 difference between 5 and 4.25. Where is that going? So back on the top here, what was that value that we used to measure growth? What did we call that? Where's it going? This might be a tough question. All right, Olivia, thank you. That is where it is going. So essentially, whatever, it's like the budget, whatever the surplus, whatever the money left over goes to, and I don't know why I made that red, biomass increase. Growth is another way of saying that, but I want you to use the term used in the POGIL. Biomass increase is where it's going, right? And This one, herbivore A, is going to have a less biomass increase than herbivore B. All right, so now let's read this. And number or letter B here, add labels. This has already been done. So essentially, biomass increase would be this small dotted arrow. All right, biologists often refer to organic matter by the potential energy that is released when the substance undergoes a chemical change to make carbon dioxide and water. So in cellular respiration, remember, those are our products. This could occur by burning the organic matter or by an organism using the organic matter in cellular respiration. Okay, so now I would say this part, 14 to 20, is kind of the challenging part of the activity. So we're going to work our way through as much of that as we can. We got 20 minutes left. So according to Model 1, herbivore A eats 4 grams of grass per day. Using Model 2, how much potential energy does this represent? And this is kind of a tricky question. So it's asking for how much energy the 4 grams represents. So how much energy goes into herbivore A in Model 2? And energy is in kilocalories. How much? Let's see what we think. Okay, so we got 1.6. 1.6, it's not going to be the one. So where did we get the 1.6 from Katie? I'm just curious. It's going to be smaller than that. It's going to be the amount that actually just goes in, right? It's going to be this 0.8. So what the question is asking essentially is, it gets 4 grams, but how many calories are contained within that 4 grams? And using Model 2, we could just say it's that 0.8. So kind of a tricky question, right? Now, number 15, according to Model 2, how much energy does herbivore A require for cellular respiration each day? So also reference Model 2. I'll give you a moment. Think about that value. Model 2. A for cellular respiration, how much? How many calories? Nice. Nicely done. So essentially, this isn't too much, it's essentially referencing what you have. It's referencing the figures. That is how much is used in cellular respiration each day, okay? Now, this is where we get into the formulas. And this might look intimidating, but it's really, I provided this to help you break it down. And that's okay what you can actually do is you could technically, and it might be kind of hard to like edit this yourself, and because this is an equation, but essentially you can just type in the following into your calculator and just get the answer and put it right here, or whatever, or 45% or 32%, whatever it ends up being. So energy lost is either heat to the environment or ingested as waste is not considered to be an efficient use by the organism. So what percentage of the potential energy, now it wants to know, is not efficiently used by herbivore A? So what we have to do is we have to take our ingested waste value plus our heat loss value over our total grass energy. So I'd like you to type this into your calculator. I'll make another equation, and let's see if, actually I think I can, let's get rid of whatever that is. I think I can copy this and make a separate equation from it. Okay. All right, I think I can do that. So ingested waste is how much from this figure? 0.33 kilocalories. Heat loss is 0.228. So we're going to take 0.33 plus 0.28. Okay, I can edit this. That's pretty. 228, I think it was. I'm trying to remember. Over total grass energy, which was our 0.8. And if you wonder how I did this equation, you can go to insert equation and play around with it. It makes it easier to create mathematical equations in Word, or I should say Google Docs. All right, so then we've got a percent. Can anyone calculate this for me? What percentage do we have as not being used efficiently? So take the top two, add them together, and divide it by this. 69.5 looks awesome, or 0.75. I'm going to round it up to 70 just to make it nice. 70%. So all you really have to do is type in, make sure you have the answer, right? You know, I'm not going to grade whether or not you could perfectly get these equations in. Just make sure you've got that percentage in, okay? So now the same question for herbivore B. We just switch over to the other figure. So we want egested waste plus heat loss over total grass energy. Oh, did not want to get rid of that. All right, so let's see. Start working on this and see if you can calculate it. I'll put in the values as we speak. So we got 1.25 and 1.4 over 5. Doesn't matter the order in which you add them. 5 calories total, and I probably should put units in here, but I'm just making it a little bit easier and less redundant by leaving my units out. 53%, Isabel and Olivia, thank you. That looks to be correct. Yes, I'm just referencing my key to make sure I'm doing things right. Good, good. So do the herbivores, and this is a key question, do the herbivores have the same efficiency in using the grass? And explain in a sentence or two. So first of all, do they have the same efficiency? Type that in the chat box. No. No, they do not. No, they're, you could say their percentages different. Thus, they are not equally efficient. And if you see here, essentially just looking at how much more herbivore B ate, 5 calories, versus 0.8 for herbivore A. But this one ate a lot more, but it was less efficient in digesting it. So it kind of got less for its money than this one did, if so to speak, right? So herbivore A and B are eaten by carnivores. Now I want to make sure, all right, I've got enough time to go through number 19. And then I'll leave probably the extension questions for you to finish for homework. All right, so herbivore A and B are eaten by carnivores. Which category of energy related to the organisms is in Model 2 is directly available to the carnivore who eats the herbivores? So what do the carnivores get? Do they get the grass when they eat the cow? Do they get the respiration? Do they get the biomass or the waste? What do they get? That's what it's asking. What do they get? So chat box, what do we think there? What does it get? Is it eating the cow's waste? Probably not. It's not eating the cow's respired energy. It's not eating the grass the cow ate. Well, I guess the grass might be in the cow, which is indirectly being eaten by the mountain lion or what have you. But yes, biomass is what they're getting. Biomass and is what it is getting. Getting the cow's meat, you would say, the beef of the cow. All right, so now we have to calculate percentages again, and this can be tricky. So what percentage of the original grass energy is available to the carnivore if it eats herbivore A? So I've set this up to help kind of scaffold and break this down. So biomass is the total calories in the grass minus the energy lost to get the calories left over. So first, let's calculate how many calories do we have left over? Right, so we've got to figure out how many total calories are there in the grass for herbivore A. 0.8, right? Total energy lost is going to be, and let's make sure we recall what that is. Total energy lost is going to be that 0.75 that we calculate as the energy output. We could also call this energy output. What are we going to have left over here? What's left over? That I want you to calculate. So type that in on your calculator. Or work it out in your brilliant minds. Good. I'm seeing 0.05 kilocalories. So that is essentially the surplus. That's the calories left over. Now what we have to do is we have to go down and use this equation essentially to figure out what percentage of it is available to the predators. So we take our 0.05 over the total calories, which is our, oh, did that again. Let's try to stop doing that. Yes, total calories, 0.8 times 100. So let's figure out what that percentage is. It's not very big, certainly not very big. So please calculate that. .5 divided by 0.05. Yes, it is 6.25%. That is how much of the energy. So it's not the traditional 10% because it's not always going to be that exact value, as we proved yesterday on our ecological pyramids POGIL. It averages out to about 11, 6.25%. So now we got to do the same thing on part C, or before B. Total calories in the grass. So how many calories were there in that grass before B? So tell me that first. I'm going to wait for you. Or feel free to shout it out. I know we're quiet this morning. 5, right? 5, good. Thank you, Wade and company. 5. What is the energy output? How much energy was lost total? What was the energy output? It's going to be that, right? It's going to be that 4.25. So that is how much it used in its body processes. So how much is left over? This, I want you to calculate right now. Calories left over for the predator to get. 0.75. Fantastic. So now we take this equation, this basic equation, which I wouldn't have expected you to just come up with on your own because that's kind of not overly intuitive. 0.75 over 5. Let's figure out that percentage now. Let's figure out that percentage. 15% I'm seeing. We'll double check that on the calculator. Not that I don't trust you, Skylar. Let's just 0.75 divided by, going to be 5. 15% times 100. Right? That's how percentages work. Okay, cool. 15%. So now the last one I'm going to go through together will be 20, and then I'm going to leave you to do the extension questions on your own. That'll be your only homework for tonight. Which herbivore is more efficient? Is the more efficient food choice for the carnivore? Which one does it get more from? And why? So essentially, this is, you got two choices. Is it A? Is it B? Which one is better eating for the mountain lion? Yeah, I'm going to go ahead and just copy exactly what Abram said and put it right in there, because that is what we're looking for. Herbivore B, because more energy can be transferred to the carnivore, because a higher percentage of energy can be transferred to the carnivore. Right. Absolutely correct. All right, so those extension questions, I will leave you to go ahead and answer those. Let me know if you have questions. Like, honestly, some of these are kind of difficult. Like, it'll just ask you to make like a grasshopper rabbit analogy, and then think about that. It doesn't. The bottom part, the extension questions, are not the important part of the POGIL. The important part is what we've walked through. So do those extension questions and turn it in by tonight. Kind of a quick turnaround, but if you've been following along, you'll be, perfectly fine because we've done the large majority of it. Okay, so let me just jump back into my presentation and make sure I didn't miss anything. Let me do that. So I think we are good. So feel free at this time, you can go ahead and leave the Google Meet. You have my permission. Last 5 minutes, you can go ahead and jump out. I'll take attendance. Ask me questions if you have any. Have a great day, everybody.